Okay everyone, welcome back to episode 2 or lesson 2 on designing a plane. Today I want to expand more on some principles of aerodynamics and how it works. But first we need to learn something, and that something is going to be called the Newton's Law. Newton's Law. So Newton's Law is made up of 3 distinct types of principles, or I should call them axioms, which basically means that they go with the motion of the earth and nature itself. So these are about how force works and how using force we can create motion. So that's the 2 main principles of Newton's law. So there's 3 laws. I'm going to go over them. Now, one thing before I say anything about these laws. You always need to have force for something to have the 3 motions of laws. Okay, you always need to have some type of force, some type of pushing force. For example, we have thrust in the plane, and another example, I'm pushing a box, there comes force. Okay, you always need to apply force to get force. Okay, so the first law is what it's basically describing is inertia. Inertia is how something moves. Okay, if it's at rest, let's say a box, if it's at rest and nothing happens to it, then it's at rest. If I'm pushing a box, then the box will be continue push. There's other things like friction, and it stops the box itself, but because I'm pushing that box, and if there's nothing else, then it would never stop. That's the same thing as like if I'm in space and I start to move in a general direction by an external force, then I keep going in that direction until something stops me. Okay? Or if I'm staying still and something moves me, okay? So I always stay here. And that kind of changing of motion is inertia itself. So Newton's first law, the textbook definition is a body at rest tends to remain at rest. So like a box remains at rest. And a body in motion tends to remain in motion at the same speed and same direction as we are talking the vectors. So it'll have the same vectors. Okay? And then, for example, an airplane at rest on a ramp will always stay on the ramp except some sort of internal force comes in and pushes it, and that external force, to overcome that inertia, that external force is essentially thrust and the turning of the propeller. In terms of a smaller general aviation plane, okay? Second Newton's law is essentially force equals mass times acceleration, okay? This law isn't exactly what Newton has written out, like the formula exactly, but it's what he described, and scientists were able to get to this point, a simplified version, okay? So force, the definition of force is mass times acceleration. That's why I wanted to talk about acceleration, okay? So a mass, let's say this plane, I was designing this plane, and it was, I'm just gonna give it an arbitrary number of 5,000 pounds, okay? 5,000 pounds, or I should write it here, 5,000 pounds, or actually, let's do 1,000 kilograms for simplicity's sake. Multiply acceleration, let's just say 50 meters per second, we can calculate the force we get, and the force is in newtons, okay? So 50, 4 newtons, okay? You won't ever need to calculate anything, but just knowing that this formula exists, and it's basically saying when a body is acted upon by a constant force, its resulting acceleration is inversely proportional to the mass of the body and is directly proportional to the applied force. So basically, Newton's second law is just this formula, the generalization of this formula. The first law is inertia. Now the third law, I would say, is quite important to aviation, is every reaction has a reaction. Every force applied has an equal and opposite force applied. So if I'm pushing a box here across this floor, there's going to be an equally opposing force in the opposite direction for every. And one of the most famous things being said about this is, for every action there is an equal and opposite reaction. For every action there is an equal and opposite reaction. So in this case, the opposite reaction would be, actually a better example would be me pushing down on a box towards the ground. The opposite reaction would, in fact, be the normal force, or the perpendicular force, up into the box. And we call this force the normal force because a force is acting upon it. There is no normal force if there is no force acting upon it, okay? So due to this, having this kind of opposite reaction, we basically get these byproducts, okay? With thrust, we have an equal and opposite reaction. We have drag. With lift, we have an equal and opposite direction. We have lift. So that's kind of an extension of what we were talking about in the last lesson, okay? And then another thing I want to talk about is something called the Bernoulli's principle. The Bernoulli's principle. So, Bernoulli's principle. I'm going to go quickly over the Bernoulli's principle. The Bernoulli principle, I believe, is one of the most incredible things that happen in a change of air. So let's say we have a venturi, and what a venturi is, it's kind of like this cone-shaped contraption. And then what it does is, as you can see, we have two outer spaces and then one inner space. And then I can draw air or any type of fluid, and air is a fluid, so know that air is a fluid. And when I'm drawing this fluid, I can represent this middle of the two with more compacted air, like a compression of a sound wave or something like that. And what this basically means is that the velocity is increased, but the pressure is decreased. And that is essentially the whole kind of act of the Bernoulli's principle, okay? So having a velocity that's increasing from a normal velocity, so velocity here is equal and pressure here is equal to the velocity here and the pressure here. They're both equal. Now the changing velocity is when it gets smaller and smaller, okay? And then when we get smaller, the velocity increases and the pressure decreases. And why is this important? Why is the Bernoulli's principle important? That's because if I take this cross-section over here, and I draw something similar, and a bunch of fluids here, what I can do is, taking this exact wing, if we take this wing and decide to create a wing foil, and it looks something like this, which I'll describe what an airfoil is, which is a wing. If we place this into this venturi, as you can see, it fits perfectly. This bottom part is in perfect alignment with this top part. And why is this important? Because we have a velocity increase and a pressure decrease, this increase of pressure of a normalized zone and a decrease of pressure here, that's what makes it lift, okay? So this is a high pressure and this is a low pressure. This is low pressure. Now what happens is, in Earth in general, just like the law of just like a normal action of everything, it wants to be in equilibrium, right? So the high pressure wants to go to the low pressure, and because of this, it's going to lift the plane up. And what this does is create a kind of an angle, and I'll talk more about that later. So that is the basic generalization of why we need to know the Bernoulli's principle. This is a very, very interesting and cool kind of fact we can talk about this Bernoulli principle. Okay, so let me quickly talk about the airfoil now. The airfoil is just this cross section of a wing, okay? This is important because this is how we calculate important things when we're designing a plane. So this dot over here is what we call the leading edge, and it's what the airflow hits first. And then after that we have upwash here. We have upwash here. Never fly into lightning, by the way, in the thunderstorm. And then we have a trailing edge here. And then after the trailing edge, we have the downwash, which I would describe over here. So if I'm drawing airflow, it would hit the leading edge first, and then it will hit the trailing edge and downwash over away. Same thing bottom here. And the pressure difference is what makes lift work. So this is an airfoil. The pressure difference is what makes lift work. Okay, so that is an airfoil, which is any surface. So an airfoil is any surface that creates lift. Okay, and a wing is just a very specific example. So it's a moving fluid and the interaction of the airflow and how it works. That's just the generalized definition of an airfoil. Okay. Now, we can break down this airfoil even more and draw a line in between that airfoil. That airfoil is going to be called the chord line. This line is the chord line, or the chord line, H. And then another vocabulary term you should know is camber. And that's basically, I like to think of it as like the shape of the wing of the airfoil. The camber is the shape of the airfoil. More specifically, it's the characteristic of the curve of the airfoils, upper and lower. So, if you want a more better definition, it's the characteristics, so basically how it acts, of the upper and lower sides of an airfoil. Okay? And then we have the angle of attack, which is the angle between the chord line and the direction of the relative wind. So when I'm talking about a relative wind here, we could talk about the relative wind. And then having this relative wind, I could have something like a flight path where a plane is flying. And something you should know about what this is called headwind. And whenever you're taking off in your airplane, you always want to fly into the headwind because it's more stabilized. And this is the flight path and this is the relative wind. And having this relative wind in this direction, and then we also have the camber, the relative wind, we create an angle. And this angle is called the angle of attack. This angle is especially important because your life is on the line because of this angle. If this angle gets too large, that's something we call a stall. And the term for when it gets too large, the angle of attack, when it gets too large, or the coefficient of lift gets too large, so the amount of lift it creates is the coefficient of lift, which looks like a capital C with a lowercase l, a subscript, is a stall. And whenever we reach something called the critical angle of attack, whenever you hear the word critical, you always think of something very important, very pertinent, very time being. And in this case, it's that exact point where the airfoil cannot have a smooth air flow over the wing, and because of this broken up airflow, you cannot get lift, and therefore you stall. Okay, we'll talk more about stalling characteristics, but stall is basically the separation of airflows from a wing's upper surface. So the separation of airflow of air on upper surface. Okay, that's basically what a stall is. And there's many different wing design factors, and you can, there's more about this theorology. It's such as something like the boundary layer or something like that. And aeronautical engineers, aerospace engineers, scientists, they experiment with airfoil designs, and they experiment with wind tunnels, see where the points of pressures are in programs, and that's all more of the college level advanced parts of designing an airplane. Okay, so that's basically what I wanted to talk about with aerodynamics. Not the entirety, but just the very first chapter of basics. That's what the aerodynamics are that we're talking about. Okay, so for this next lesson, I'm going to go more about design aspects and more about how we can design a plane. More specifically, aspect ratio, wing area, how that affects the airplane itself, how much lift it provides. Talk about many shapes of an airplane, that's called a plan form. The shapes of an airplane is spectacularly important because you need to know the shape of what you want to build. Even with something as similar as as simple as a paper airplane, we have something of such similar, of such airfoil here. This plan form here is much different from a plan form of here. You can see this one is kind of swept back, while this one is a little bit fixed up and a little bit broad. Okay, so having these two are great examples of how they each fly. This flies like that, this flies like that. Okay, so having these types of different knowledges will help you in better designing your plane. And we can finally settle on a design of this plane, which one will work better for in terms of a corporate jet and kind of the requirements we need. For example, the requirements we need of carrying passengers, carrying fuel over a long distance for like a business trip, and we'll all figure out that in the next lecture, in the next lesson. All right, thank you very much. We're we have the knowledge to get closer to learning how to build and design a plane. So by the end of all of these videos, I hope to actually teach you and teach myself how to build a plane, something out of materials. We'll talk about that, like cardboard, how to use knives, X-Acto knives to get it precise. And then we'll also bring in some RC planes to talk about the aerodynamic factors and how those work too. All right, thank you. Have a good day.